Imagine harnessing the power of the sun, not with solar panels, but by recreating the star's inner fire right here on Earth. That's exactly what scientists in China have been working toward. And in early 2025, they reached a major milestone: 1,066 seconds of sustained, high-temperature plasma inside their East fusion reactor. That's over 17 minutes, a new world record, and a huge step toward practical fusion energy. Welcome to Elemental Science Magazine. Imagine harnessing the power of the sun, not with solar panels, but by recreating the star's inner fire right here on Earth. That's exactly what scientists in China have been working toward. And in early 2025, they reached a major milestone: 1,066 seconds of sustained, high-temperature plasma inside their East fusion reactor. That's over 17 minutes, a new world record and a huge step toward practical fusion energy. Fusion energy has long been the holy grail of clean power. It promises near-infinite energy, zero carbon emissions, and none of the meltdown risks associated with today's nuclear reactors. But achieving it is one of the hardest challenges in modern science. That's what makes this 1,066-second run so significant. In this video, we'll explore what the East Tokamak is, how it works, what makes this record important, and how it stacks up against other major projects like ITER and the National Ignition Facility. And most importantly, we'll look at what it all means for the future of energy, industry, and our climate. Fusion energy has long been the holy grail of clean power. It promises near-infinite energy, zero carbon emissions, and none of the meltdown risks associated with today's nuclear reactors. But achieving it is one of the hardest challenges in modern science. That's what makes this 1,066-second run so significant. Let's start with the basics. Fusion occurs when light atomic nuclei merge to form a heavier nucleus, releasing massive energy. It's what powers stars. Here on Earth, to do that, we need to heat hydrogen fuel to over 100 million degrees Celsius, turning it into plasma, a hot, ionized gas, and then hold it in place using magnetic fields. But here's the catch: you can't let that plasma touch anything solid. At those temperatures, it would vaporize metal. So, fusion reactors use magnetic confinement to suspend the plasma inside a donut-shaped chamber called a tokamak. A tokamak creates a powerful magnetic cage. Coils wrapped around the chamber generate toroidal and poloidal magnetic fields that twist into a helical shape. This is what holds the plasma in place. Inside this chamber, plasma flows like a controlled lightning bolt, and researchers fine-tune heating systems and magnetic fields to keep it stable. But plasma is unstable by nature. It writhes, leaks heat, and tends to collapse if not perfectly balanced. So the challenge isn't just making fusion happen, it's keeping the plasma alive and confined long enough for it to generate meaningful energy. And that's where East comes in. China's experimental advanced superconducting tokamak has been pushing boundaries since 2006. It was the first tokamak to use superconducting magnets for both major magnetic fields, allowing for longer pulses without overheating. In 2025, East managed to sustain a high-confinement plasma, not just any plasma, but one in H mode, which is more stable and efficient, for over 17 minutes. That's more than double the previous world record, and it did so at over 100 million degrees Celsius. That's hotter than the core of the sun. How did they do it? Upgrades. Since previous runs, East doubled its heating power, improved its magnetic control systems, and refined its plasma-facing materials to handle the extreme conditions. Despite pumping in the equivalent energy of 140,000 household microwaves, the plasma held steady, a major feat of engineering. This wasn't a net positive energy run. They still used more power than the fusion generated. But that wasn't the goal. The goal was control, stability, and duration, and they achieved it. Let's compare. ITER, the International Fusion Mega Project in France, aims to produce 500 megawatts of power from 50 megawatts of input, but it won't begin fusion tests until the late 2030s. In the US, The National Ignition Facility uses lasers instead of magnets. In 2022, it made headlines for briefly achieving fusion ignition, getting more energy out than went in. But that lasted just billionths of a second. ITER, on the other hand, is all about sustained performance. It didn't ignite, but it kept the plasma stable and confined for over 1,000 seconds. It's endurance versus peak power, and both are needed for real-world fusion. Why does duration matter? Because future fusion power plants must run for hours, days, ideally without stopping at all. The longer a plasma can be held, the more energy it can produce, and the more reliable the reactor becomes. Short pulses waste energy and wear out components. Long pulses simulate real conditions for future reactors, testing how materials hold up, how heat can be exhausted, and how magnet systems perform over time. ITER's 17-minute pulse proves that steady-state operation is within reach. So what does all this mean for the future? Fusion could provide near-infinite energy from seawater. It emits no carbon dioxide. It produces no long-lived nuclear waste. It can operate day and night, regardless of weather, complementing renewables like solar and wind. As the world races to decarbonize and meet rising energy demand, fusion could offer the ultimate backup: clean, safe, and scalable. But we're not there yet. Fusion still faces major engineering challenges: breeding fuel, developing durable materials, and building reactors that actually feed energy to the grid. But the momentum is growing. Projects like ITER, and NIF are breaking barriers. Private companies are designing compact reactors. Governments are investing billions. And the breakthroughs are no longer decades apart. They're coming yearly, sometimes monthly. Fusion is transitioning from theory to engineering, from physics to industry. China's 1,066-second fusion plasma run is more than just a number. It's a signpost, a signal that we're inching closer to a future powered by the same force that lights the stars. Fusion energy won't solve tomorrow's energy crisis, but it could define the world beyond 2050. And milestones like this are writing that future, one pulse at a time. If you found this fascinating, follow for more deep dives into the science shaping our future. And let us know, what would you power with limitless clean energy? Until next time, keep your eyes on the stars and your feet on the power grid. Subscribe to Elemental Science Magazine